Okay, recording has started. I've shared my screen. Guys, please do let me know when you can see the screen. Can you guys see the screen? Please do let me know if you can see the screen.
Yes, sir.
Okay, thank you for that response. So, in the last class, we have seen these things: the performance of the computer, response time, throughput theories, relative performance, formulas, and some problems as well related to these topics. Next, in these theories, elapsed time, CPU time, and what are the difference in these two. And we also have seen clock period, clock frequency in here, and we have seen this formula for CPU time with clock cycle time and with clock period as well. And we have seen some problems as well with that. And we have seen a new formula to divide clock cycles into new.
স্যার আপনার কথা শোনা যাচ্ছে না।
No, you cannot hear me. Please respond.
স্যার কেটে কেটে আসতেছে।
My internet connection is perfect. What is the problem? You still cannot hear me properly. My voice is crumbling.
স্যার এখন ঠিক আছে, কিন্তু একটু ভাঙা ভাঙা মাঝে মধ্যে মনে হচ্ছে।
Okay, okay. Do let me know when you can hear me properly. Because I think my internet connection is okay. All of you should hear me perfectly.
স্যার কথা শোনা যাচ্ছে কিন্তু স্পষ্ট না আর কি।
Because of the internet connection, maybe I don't even know what is the problem. Okay, let me switch to mobile network. If you guys are having problem hearing me over the Wi-Fi connection, better I switch to mobile network. Okay, just give me 1 minute. I'm going to switch to mobile network, and then I'm going to ask you whether my voice is clear to all of you or not. Okay, just wait.
Yes, sir.
Hello, everyone. Can you hear me now? Now I am connected with my mobile,
Yes, sir. We hear you.
my mobile data. You can hear me properly now?
Yes, sir.
Okay, okay.
জি স্যার।
I can continue now. Just wait. I have shared my screen. Do let me know when you can see the screen. Okay. You can see the screen.
Yes, sir.
Okay. So in the last class we have seen these things like the formulas of CPU time to calculate the clock cycles, and in the last part we have seen this problem where a table was given and we have to calculate the average reply for two code sequences. So we have done this perfectly. I think there is no confusion in the previous class part. Today we are going to see two topics in here. One is actually the power wall topic. We are going to cover this at first, and this is all related to theories. Okay, no problem with any kind of formulas in here. There is a formula for power given, but no kind of problems we are going to solve with that. And there is a Amdahl's law in here. There is a formula. We are going to find solution of few problems with that. Okay. So one formula with a problem, and there is a theory of power wall. These are the two topics of this class lectures are left, and that is the only part will be included in this class for the CT1. Okay, and I'm going to talk about the CT1 schedule as well, because in the last class we have decided that we are going to take the class test one before the Eid vacation, and uh, in the section A as well. Sorry, this is section A. In the section B, which has classes in Saturdays and Tuesdays, they have decided that they are going to give the class test one before the Eid vacation as well in the previous class. But uh, yesterday, uh, section B students decide against their idea again, and they wanted to give the class test one after the Eid vacation. Okay, so most of them have voted for after vacation, as they have many class tests before the Eid vacation. So now I am going to ask you again, because I cannot do that. I cannot take your city before Eid and their city after the vacation. I cannot do that. I have to take this in a week. Okay. So I'm going to ask you again to let me know what you guys feel about that. Okay. So we are going to decide about that after we end taking this class, after we finish taking this class. Okay. So now only concentrate on power work. Okay. And whatever the schedule is before Eid or after Eid, I'm not going to change the syllabus for that. Syllabus will be up to this for CT1. Okay. There will be no change in the syllabus. So just let me go through these slides first. Okay. So power wall, we are going to talk about power. Okay. So this is the formula for power. And do not ask me where it came from, because I'm not a physician, or I cannot tell you about how this formula is generated, and few terms as well. For example, this is capacitive load in here and it is fixed. And do not please ask me why it is fixed, why it is constant, because this is the part of the physics. Okay. So I'm not going to talk much about that, but what we have in here, that this is the formula of the power we are going to follow. Okay. We are going to talk about power, but we are going to talk about the enhancement in the performance of our computer as well. Okay. What we want in our computer, we want to enhance the performance. And you guys have seen in the previous class that this is, sorry, this is clock frequency or clock rate. This is the performance of the processor. If it is more, our performance is better in the computer, right? You have seen that clock frequency. And in the power formula, you can still see the frequency in it. Okay. So in this power formula, we can clearly see that there is a frequency part in it. Okay, so this load, capacitive load, is fixed, then it is multiplied with voltage square, then with frequency. So if we want to increase or enhance the performance of our computer, we have to increase the frequency, right? Please respond.
Yes, sir.
Okay. And for example, if we keep on increasing the frequency, this power will rise up, right?
Yes, sir.
And if this power uh, gets to its limit, so that we cannot increase any more frequency. For example, if we increase frequency a bit more, power will exceed the limit. And if power exceeds limits, what will happen? Our computer will hang up or freeze. Our registers may burn, so it will stop working. So we cannot increase the power more than of its limit. Okay. So we have to increase the frequency in such a way that our power does not exceed the limit. Okay. So for example, if for some frequency, for example, for 1000 frequency, our power has reached its limit, which is 30. This is just an example. For 1000 frequency, our power has reached its limit, and which is 30. So can we increase the frequency?
No, sir.
No,
No,
sir.
we cannot increase the frequency, but we still want to enhance the performance of the computer. And we only know one thing in this formula: if we increase the frequency, only then we can improve the performance of the computer. Now we cannot increase the power, so we cannot increase the frequency. But in this formula, frequency is not the only variable. As you can see, this is the constant in here, capacitive load. We are not going to talk about that. But voltage and frequency are both variables in here. So we can change both of these things. Now, if we increase the frequency in some manner by decreasing the voltage so that power doesn't rise, can we improve the performance of the computer?
Yes, sir.
I am going to repeat the line again. Our idea is to increase the frequency in such manners by decreasing the voltage so that power doesn't rise. Okay, for example, if we decrease the voltage by 2, actually we are decreasing 4 because it is voltage square in here. If we are decreasing the voltage by 2, we are decreasing the voltage by 4. We can increase the frequency by 4 as well, right?
Yes, sir.
So that power doesn't change, power doesn't rise. So if we somehow find a way that we can increase the frequency with decreasing the voltage, that power doesn't rise, we can still enhance the performance of our computer, right?
Yes, sir.
From 1982 to 2007, they have tried this way. They have decreased the voltage a little bit and increased the frequency a little bit in such a way that power doesn't rise. In this way, they have carried on this legacy to enhance the performance of the computer and kept on doing until it is 2007. After 2007, they have decreased the voltage so much to 1 voltage that they cannot decrease it any further. From it initially it was 5 voltage. Okay, initially it was 5 voltage. Then they used to increase the frequency and decrease the voltage to maintain the power, and they have decreased the voltage from 5 to 1 voltage. And after 2007, they have now decreased the voltage up to 1 voltage. And what is this voltage is actually? These voltages are required to turn on or activate the registers of our processor. If it doesn't activate the registers of our processor, our computer will not work. So they have found out after 2007 that they cannot decrease the voltage further. Why? Because if they decrease the voltage from 1 voltage, registers will not turn on or our processor will not be activated. Okay, so we cannot decrease the voltage further. So can we improve the frequency any more? Because we cannot change the power, we cannot make any rise in the power. So if we cannot decrease the voltage further, can we increase the frequency?
If we decrease the capacitive load, then we can increase the.
No, no, no. This is fixed.
Okay.
We cannot change that. This is constant. This is constant. We cannot decrease the voltage further. Can we improve the frequency?
No, sir.
So after 2007, they have realized that they cannot improve the performance of the computer anymore, as they have to use this formula where this load is fixed. They cannot decrease the voltage, they cannot change the
স্যার
power, so they cannot improve the frequency. Yes, yes, yes.
স্যার এখানে স্যার যে ফ্রিকোয়েন্সিটা বলা হয়েছে স্যার এটা কি একটা কোরের ক্ষেত্রে বলা হয়েছে স্যার এখন তো মানে
Yes, yes, for a single core.
কোরগুলো বাড়ানো হয়েছে অনেক বেশি
Yes, I'm coming to that topic. So up to 2007, they have found out that they cannot improve the performance of the computer anymore. But from 2007 to this 2021, computer have improved. The performance of the computer has improved, right?
sir.
Then how they did that? One of them already answered that
কোর বাড়ায়
after
দিছে
after 2007 they have realized after 2007 they have realized that for a single processor, whatever the frequency they got by decreasing the voltage up to 1 voltage, that was the maximum performance for a single processor. After 2007, they have decided that whatever the frequency they got by decreasing the voltage up to 1 voltage, that was the maximum performance for a single processor. So they cannot improve the performance of a computer if they do not introduce more than one processor or one core in it. So this was the problem, and after 2007, you can see core to do or dual core was introduced to resolve that problem. And this is the problem for the uniprocessor performance, as we cannot improve the performance anymore after decreasing the voltage up to 1 voltage. And this problem is being solved by introducing this multiprocessors. Okay, or multi-core microprocessors, whatever we say. So what is Powerwall? We cannot reduce the voltage further, we cannot remove more heat. And how to overcome this Powerwall situation? We have to introduce multiprocessor. So is this Powerwall topic perfectly clear to all of you?
Yes, sir.
Yes, sir.
Okay, so I can move to the next topic, that is Amdahl's law in here. Okay, this is interesting as well. You will find it much more easier. So you have seen in the last class that I have shown you an example of adding two numbers in the calculator, and you guys know about what is elapsed time and CPU time in that. Okay, we are going to talk about that later in this example in here. Okay, so Amdahl's law says this is the formula to find out the improvement factor. Okay, time improved, time affected, time unaffected, and this is the improvement factor we are going to find. There is an example problem given. Multiply accounts for 80 seconds out of 100 seconds. So they are saying, for example, if I want you to multiply two numbers in the calculator application, that calculator application is taking 80 seconds to multiply out of 100 seconds I am using. So for example, I am taking 20 more seconds to give the input. Okay. So actually our calculator application is taking 80 seconds out of 100 seconds I need to multiply two numbers. Now they are asking how much improvement in multiply performance, only in multiply performance, only in this 80 seconds we can get to get overall 5x improvement, and that 5x is time improved. So total time is 100 seconds in here. So first thing we are going to know is what is this time improved is, then we are going to know what is this time affected is, then we are going to know what is this time unaffected is. If you understand these three parts, we can easily find the improvement factor. The given problem is asking us to get 5x overall improvement. So overall means in the total time, we want 5x improvement. Total time was 100 seconds to complete the task. Total time was 100 seconds to complete the task, and they want us to solve this problem with 5x performance better. So we are going to divide this 100 by 5, 100 by 5, and we are going to get this 20 in here, this 20. So this 20 is time improved, total time divided by the amount of time we want to improvement in total. We want 5 times more improvement, so we have to divide 100 by 5. This is time improved. So is there any confusion related to time improved?
স্যার এখানে 100 সেকেন্ড কি ইউজার ইনপুট সহ?
Yes. Total time, elapsed time, and 80 seconds is the time for CPU time, only to multiply two numbers. And okay, if you get this time improved perfectly, let me know, tell
Sir.
you. What is time? Yes.
Can you repeat this again? I'm not.
Time improved is the total time 100 divided by the amount of times we want to improve 5.
The total time
100,
after five times improvement.
yes, 100 divided 5 is this 20. This is time improved. Is it
Okay.
clear? Okay. So we have to know what is time affected and time unaffected. I'm going to give you the definition, then you are going to find what will be the values for it in this problem. Time affected is the time we can improve with any modern technologies or a good algorithm or a better algorithm. For example, in here, the 80 seconds we require to multiply two numbers, if we use a better processor, it might be 70 seconds to multiply two numbers. If we use a better processor with modern technology, we can improve this. And uh, for example, we are using a better algorithm to multiply two numbers, and that algorithm takes only 60 seconds to multiply two numbers. So, if time affected is the time that we can improve with better technologies or better algorithm, that is time affected. So, in here, the time affected is 80, and the time unaffected is the time we cannot improve it with any kind of technologies or the algorithm. For example, if I write a better algorithm, if I write a better processor, I can still take 20 seconds to give that input, right? It cannot
Yes, sir.
improve me as a user to give
Yes, sir.
input faster, right? It has to wait for me to give the inputs. So no algorithm or no technologies can improve me do that. So this is time unaffected. We cannot affect it with any algorithm or technologies. We can affect this time with technologies or algorithm. So can we just differ these two things and understand why this is 80 and why this is 20?
Sir, 80 is the CPU time for,
Yes, yes, yes.
and time unaffected is 100 minus 80.
100 minus 80. Overall time minus the affected time. That is very
Yes, sir.
good. Okay, fine. So if in a given problem, we can identify these three terms, time improved, time affected, time unaffected. Can we find the value of this improvement factor n? Can you find this? Can you guys hear me? Okay, you guys
Yes,
can hear me. So, can we find the value of n in here? Please do respond.
Yes, sir.
Okay. If we find the value of n in here, and if somehow we find the value of n as negative or indeterminate or infinite, then we are going to say it is not possible.
স্যার এখানে তো এটা হবে না, পসিবল না স্যার।
Yes, yes, yes. And how we are going to say that improvement is not possible after finding the value of n? Remember, if we somehow find out the value of n as negative or indeterminate or infinite, we are going to say it is not possible. The improvement, 5x improvement is not possible. But somehow, if somehow we get n value as positive, we are going to say for that n value, 5x overall improvement is possible. Is it clear to all of you?
ইয়েস স্যার।
For example, if I have given 4x instead of 5x, what
দেন
would
ইট ওয়াজ
have
পসিবল।
happened? Because this would have been 25, right?
ইয়েস স্যার। দেন
And the
5
value
সেকেন্ড
of
ইজ
n,
দি
value, if we calculate, the value of n would have been 16.
ইয়েস স্যার।
Value of n would have been 16. I'm not going to give explanation of that, how it is 16. You can find that from this expression. If this is 4x, this will be 25 and this will be 16. And then we can say for improvement factor 16 or improvement factor n is equal to 16, we can find 4 times overall improvement. And now for 5x, it is not possible. Is it clear?
ইয়েস স্যার।
Okay, okay, fine. So I'm just going to finish this chapter in here. Nothing more I need to show you, but you need to remember that these two parts, Powerwall, this Powerwall, and this Amdahl's law are part of the class test one. Okay, and I'm going to close this slide in here, and whatever I'm going to show you now is not part of the class test one, even it is scheduled in the upcoming Sunday or after its vacation. Doesn't matter, whatever the schedule it is, syllabus will be same. Okay, so now this is the lecture 4. I have uploaded already in the LMS. I'm going to talk about this in here. So again, the number of instruction you can see in here, and out of this, in the category section, we have seen only arithmetic and logical up to now, right? We have seen what is add, subtract from the arithmetic. What is this and or not, and immediate or immediate, shift left, right, logical instructions. In today's class, we are probably only going to see data transfer instruction, load word, stored word. If enough time, we may see this conditional and unconditional instruction. Okay, so this is data transfer instruction in here. We are going to see, and this is load word, store word. Remember, this data transfer instructions will only be used in case there is a array in the C code. In case there is a array in the C code. So let me show you, sorry, in the next slide, that these are the two instructions we are going to talk about: load word, store word. Okay, so before that, I'm going to talk about one theory is in here. Theory is spelling. What is the spelling register? Okay, spelling means emptying the register. If we want to empty the registers, that is spelling registers. Okay, so why we need that and what is that? Okay, for example, let me tell you, we have 32 registers in our mix architecture, and each of them is of 32 bits. We know that. Now there were many kinds of register in this 32 registers, but we have seen only three type of registers: saved registers, temporary registers, and zero register. We have seen only these three type of registers. Uh, and out of these 32 registers, there are only 8 saved registers. Probably there is only 8 saved registers. And if there is only 8 saved registers in a program, for example, in a program, if there is 9 variables declared, 9 variables, then how we are going to store these 9 variables in those 8 saved registers? Can anyone please tell me? Because we know for declared variables, we have to use the saved registers. We cannot use any other registers except for the saved register. So like we cannot store the 9th variable in the temporary register by saving the first 8 in the first 8 saved registers. So if we have 9 variables, we have to store these 9 variables in the 8 saved registers only. So how can we do that? Any suggestion?
Can we do any mathematical operations?
No. By doing any mathematical operations, but we are going to do that by the help of the stack. Those who have completed the data structure algorithm course must know what is stack is, right?
Yes, sir. Yes, sir.
So the process is, for example, we have 9 variables and when we have 8 saved registers, we are going to store the first 8 variables in the 8 saved registers. Then when we have the 9th variable to store in the saved registers and we have no saved registers left, then we are going to use one of them from the previous 8 saved registers. For example, in the first sub register $S0, we have stored the first variable. Now we are going to keep that value of the sub register, take that value from the sub register to the stack. We are going to push that value onto the stack. Then we are going to store the 9th variable onto the saved register so that we cannot lose the first variable's value by putting it onto the stack on our memory. Is it clear?
Yes, sir.
Okay, so this is the process of putting less commonly used variables or those needed later into memory or stack is called spilling register. It is emptying the register. Okay. So this is how we are going to, if there is 100 variables, doesn't matter, we are going to use it like this by keeping the values of the variables onto the stack. And whenever we need the variables value back, we are going to put it back from the stack to the register. Okay. So now back to the next topic. This is the C code in here. A12 is equal to H plus A of 8. A12 is equal to H plus A of 8, and we are going to see how we can convert this codes. Assume variable H is associated with register S2, so variable H is in $S2. The base address, I'm going to talk about that in the word file. The base address of the array A is in $S3. Okay, so we don't have the complete address or the location stored in a register, but we only have a single address in a register stored for the base address of the array. And what is the base address of the array? Okay, remember the base address of the array is actually the address of the zero number index. So if I am saying I have declared an array A100 like this, and in the $S0 we have the base address of this A array. So actually in the $S0 we have the address. Remember, we have the address, not the value. We have the address of the index 0 in the $S0 register. So is that clear? What is base address of the array is?
Yes, sir.
Okay, so now if I have declared this type of arrays in here, for example, A is equal to 100, I can have index from 0 to 99, right?
Yes, sir.
Okay, for example, we have values like this 20, 37 in different indexes up to 99. Okay, we have different values in different indexes. We have to know what is offset is. Okay, so okay, let's wait. So offset is the index number into 0 or index number multiplied by 4. Index number into 4. Index number into 4. Index number into 4. So offset for 99 number index is 99 into 4. And why we need the offset? Remember, this is an integer array, right? So this is an integer value, right? Please respond.
Yes, sir.
We can store this value 20 in S1 register as well if we want. For example, I want 20 to be assigned into register S1. I can do that, right? I
Yes,
can,
sir.
for example, if this is the code, int A is equal to 20, and I am asking you that A is in $S0, so I have to store 20 in $S1, right? If A is in $S1, we can do this, right? 20 will be
Yes,
in
sir.
$S1. Okay.
Yes, sir.
We have to know we have 32 registers in main, and each register is of 32 bits. Each register is of 32 bits. Do not confuse in between these 32. This is the number of registers we see in maps, and each register is size of 32 bits, and 8 bits is 1 byte. So actually 32 bits will be 4 bytes, and 4 bytes is equal to 1 word. Remember, this S1 register will have 32 bits in it. So if we want to keep 20 in S1 register, this 20 will be converted into 32-bit binary, then is stored in this S1 register. Is it clear how this
Yes.
20 is
Yes, sir.
kept in the S1? So this 20 has the size of an integer, right? As this is integer array, every value is an integer itself. So this 20 is also an integer, right?
Yes, sir.
So this 20 will have the size of 32 bit or 4 byte or 1 word, right?
Yes, sir.
So if this 20 has the size of an integer, and if our memory is byte addressable, remember in the memory we get the address in bytes. The memory is byte addressable, not even in word, not even in bits. Our memory is byte addressable. So can I say if this 20 takes 4 bytes, the value in the index 1, this 30, is 4 bytes far from the first index 0, or
Yes, sir.
4
Yes, sir.
bytes away from the first index. Can we say that?
Yes, sir.
Yes, sir.
Okay. So offset is the distance from the 0 number index. Offset is the distance from the 0 number index. So can we say this index number 1 is 4 bytes, 1 into 4 bytes away from the 0 number index
Yes, sir.
using the offset.
Yes, sir.
99, if I ask you to find the 99 number address, so can I say 99 number index is 99 into 4 bytes away from the 0 number index? Can we say that?
Yes, sir.
If I give you this address, for example, I am saying the 0 number index has the address 2000. So this 2000 is the address of the base address, right? Because the base address of the array is the 0 number index address, right? So if
Yes,
I
sir.
say this 0 number index has the address of 2000, this is the address of base address. If I add offset with it in the index 0, you can see in the index 0 offset is 0 into 4. Remember, this is the base address 2000. Offset is 0 into 4. So 2000 plus 0 is 2000. So we can visit any index of the array using this formula, base address plus offset. Because if I say 99 number index is 99 into 4 bytes away from the first index, if we know the address of the first index, we can add 99 into 4 to reach to that index, right? Please respond.
Yes, sir.
So, what will be the address of the next index? Base address plus offset. Remember, base address plus offset. Base address is the address of the 0 number index, and this amount is the distance between 0 number index to that index. So, one number index will have the address of 2004 if the base address is 2000. Second index will have the address of 2008 using this offset and using this formula base address plus offset. So, for example, if I want to access this index A98, can you please tell me what will be the formula in here?
So
If the
base
base,
address plus 98
uh,
into 4.
so it will be 2000 plus 98 into 4 in this way, right?
Yes, sir.
Got you. 2000 plus 98 into 4. So this will be the address of 98 number index. Okay. Okay. So we can access any index having the base address by calculating the offset, right? If we have the base address and
Yes,
if
sir.
we can calculate the offset, we can reach any index, right?
Yes, sir.
Okay. By adding base address with the offset. And how we are going to calculate the offset? Remember, offset is index into 4. Offset is index into 4. Now, in this problem, the 12 number index, how can we reach that if we have the base address in $S3? Can we say $S3 plus 12 into 4 to reach into this index?
Yes, sir.
Can we say $S3 plus 8 into 4 to reach into A8?
Yes, sir.
Okay. So now we know how to calculate the uh, index address, any index address. For example, if I want to find you 99 number index address, you are going to say whichever the register has the base address, we are going to add 99 into 4 with that to find the exact address of the 99 number address. So this is how we are going to access any index of that array. Now I need to let you know how this load word and store word instruction works and what is the format of it. Remember, load word is the instruction that we are going to use when we are going to fetch any information from the any value from the memory to the register or array to the register. Then we are going to use load word. For example, if we want to read the value of any index of an array, we are going to use read. If we want to write any value onto an array or an index of the array, any index of the array, then we are going to use write. If we want to store the value, we are going to use store word. If we want to load the value from array to register, we are going to use load word. So remember just these things: read is load word, write is store word. Now, if you look at these operations in here, just let me delete these lines in here. If you look at these lines in here that we need to convert to mix only this line A12 is equal to H plus A8. Can you please tell me this A8 we are going to read this index value or we are going to write onto this index? Read or write in this index? Can you hear me? Hello.
Yes.
sir.
So you guys please tell me, we are going to add H with A8 or the value of A8, then we are going to store the value onto A12. So are we going to write something in A8 or A12?
So
Where
right,
we are
right.
write in which index, A12 or A8?
So A12.
A12.
A12, sir.
In A12 we are going to write something.
Yes,
So
sir.
in order to write something in here, we have to read this value to add with H, right?
Yes,
Yes,
sir.
sir.
So for A8 we are going to use load word for read, and for A12 we are going to use write store word. Okay, so before we use this instruction, we have to know how this instruction is being written and or what is the format of this instruction. So load word and store word has the same format. First we have to write a name of the register. Normally it is temporary register. Normally it is temporary register. Load word or store word, whatever it is, the format is same. Okay, the format is same. It is register first. Then we have to write down the offset. Then in the first bracket, we are going to write down the base address of the array or the name of the register which has the base address of the array. Okay. So first thing we are going to do, we are going to read this value of A8 using the load word instruction. Now, first thing we are going to write, we are going to use a temporary register T0. Now, comma, then we have to write the offset for this index. By looking at this offset table, can you please tell me what will be the offset for this 8?
8 into 4.
So 32.
Yes, sir.
And which register has the base address of the array A? $S3 according to that
Yes, sir.
problem.
Yes, sir.
$S3, H is in $S3 and A is in $S3, base address of the A. So now this is a completely done instruction. So what it will do, I'm going to give you a comment for that. You need not to give any comment. We are going to store the value of this A8 onto the register T0, right?
Yes, sir.
This is the operation we have done in here using the load word, right? So we
Yes,
are
sir.
going to add this 32 with the base address to access the index number 8, and then we are going to read that value and store it in the T0 register. Then we have to add this H with the value of A8, right, which is in T0. So we are going to use the add instruction in here. We are going to use another temporary register. If you just get confused using the same temporary register, so T1 in here, in T1 we are going to add H plus A8. So H was in $H2 and A is in $T0, A8. So in here what we are actually doing in the $T1, we are storing the value of H plus 8. So is it clear? Please respond.
Yes, sir.
Okay, so in the next line, we are going to store the value of T1. We are going to store the value of T1 onto a 12 number index. So we are going to write this value onto a 12 number index. For that we have to use store word. So we are going to use store word in here. We are going to write the register as the format says. After the name we have to write the register. So dollar T1 in here. The value we want to store in A12. Then offset. For 12, what will be the offset?
12 into 4, 48.
And then the base address of the array is in $S3. So after this operation, actually we are doing this in here, that in A12 it will be the value of $T1, right?
Yes,
$T1
sir.
has this value. Okay, so this is it. I'm going to give you this solution in the chat box in case you need. Do not worry, I'm going to upload this Word file in the LMS as well, so you can have that whole Word file. So I guess there is no confusion in any part that I have discussed until now. Any confusion?
No, sir.
Okay, if there is no confusion, then it is fine. So we can move to the next topic, that is we have to find the solution for this problem. Okay, and okay, this is correct. We have to find the solution for this problem where h is equal to 230, a of 10 is equal to h plus b of I, and then h is in $S2, the base address of a is in $S3, the base address of b is in $S4, and I is in $S0. So you have to find the solution for this C code converted to MIPS code. Okay, so keep trying. If there is any confusion, I will let you guys know. So I am giving you 10 minutes to find the solution. If you can't, I will give you the solution after that. Okay, so do find me the solution. If you need more time, then just please ask for it. Okay, so I'm only going to share this word file with you so that I can track in the chat box. Those who will solve this problem, do let me know in the chat box by writing done so that I can understand that you have solved this problem. Remember, you have to solve this problem in here. Okay, do solve this problem in here and let me know when you are done. So I'm waiting for your response. In case you have any problem in the question, do let me know. Okay, Mohibal Hassan, good. You have given the solution of yours. I'm going to let you know if there is any mistake after 5 minutes. Okay, some of you have tried. Should I give you more time, or I should provide you the solution? You guys please tell me. Should I give you more time to practice and try and let's see what you guys do, or should I just give you the solution? So all of you, we are not going to use the multiplication instruction. Okay, we are not going to use the multiplication, but those who have tried, at least they have the insight of the problem that we need the multiplication in here. Very good to all of you. So somebody has to respond. Should I give you more time, or should I provide you the solution?
করে দেন তাহলে ভালো হয়।
Okay, 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 okay. Let me share my full screen then. Just wait. So this was the question. Let me drag it a bit to the next page. Okay, now it is perfect. So I'm going to delete everything is in here. Okay, now I'm going to show you the solution again. Okay. So H is equal to 230. Is there any confusion converting this to make add I dollar H is in dollar H2, H is in dollar H2, then dollar 0, 230. Is there any confusion in this instruction?
No, sir.
No confusion? Okay, fine. So next instruction will be to complete this line in here, and for this operation we have to add H plus BI, then store the value in A10. Now we don't have to use any index in here, as there is a variable given and we know the address of this variable is in, sorry, the value of this variable is in $H0. Okay, so we have to fetch this value of BI from the array to register. So we have to read this value. So we have to use load word, right? Load word, and we have to fetch this value in, for example, T1 register, and we have to give the offset in here, and then we have to give the base address of the B array, which is $H. Now you guys please tell me what will be the offset in here. What will be the offset in here? Can you guys, anyone please tell me? Can anyone please tell me what will be the offset?
Index number into 4.
Normally, if there was 5 in place of I, 5 in place of I, we would have written 5 into 4 20, right?
Yes, sir.
But it is I in here. So what it should be in here? It should be at least I into 4, right?
Yes, sir.
But does our instruction knows what is I? No.
No, sir.
So it should be $S0 into 4.
$0 into 4.
But we still cannot write it. Either we have to write a register in here, or we have to write a constant value in here. Remember, this offset can be written as direct integer value or a register. Now, as we cannot write any integer value in here, as we do not have the value in here, we do not know what is the value of I will be, we have to write a single register in here. And what register it will be? A register that will have the value of S0 into 4, right? And we
Yes,
have seen a instruction to do that. In the last lecture, I have shown you that if we shift left, we multiply by 2, right?
yes,
If we
sir.
shift left one times, we multiply by 2. For example, if we shift left I one time, one time, we get I into 2, right? Is it
Yes, sir.
correct?
Yes, sir.
If we shift left I 2 times instead of 1, 2 times, then we get I into 2 into 2. right?
Yes, sir.
Because every time we shift left, we multiply the value by 2. So if we shift left 2 times, we get this one. If we shift left 3 times, we get this one. So if we shift left 2 times, we are actually getting I into 4, right? Please respond.
Yes, sir. Yes.
So if we use this instruction in here, shift left logical, in $T0, we are going to shift this $S0, which is I, 2 times.
Sir.
Hello, can you guys hear me? Hello.
Yes, sir.
There was the internet connection problem, so just wait. I'm going to share my screen again. So is it clear to all of you? This shift left operation, do let me know.
Sir, your network is not stable.
It's available. So I am using the mobile data. I cannot do any more. My network is stable or not? You guys do let me know. Can you hear me properly?
Now it is good, sir.
Okay, okay. So you got this instruction perfectly, you guys. Shift left logical T0 S02. Is it clear to
No,
all
sir.
of you?
Before your internet disconnection, we were
Okay, so
in I.
you have seen this line. You have seen this line. Shift left I
Yes, sir.
2
Yes,
times.
sir.
We are going to get I into 4. So we are going to
Yes, sir.
shift left this S0 2 times to get S0 into 4 onto the register T0. Okay. Now
Okay,
is
sir.
it clear? Okay.
Yes, sir.
So can we use this same T0 register here in place of this S0 into T4? S0 into 4? We can use this, right?
Yes, sir.
Now we are going to what we have done in here. We have stored this B of I in T1 register. In here, in the T1 register, we have stored B of I. So now we need to add H with BI. For that, we need a add instruction. In another temporary register, we are going to add H, which is in $S2 with $T1, which is BI. So is it clear? Please respond. Is it clear?
Yes, sir.
Okay, now we are going to use store word to store the value of this addition onto a 10 number index. So store word register first, then offset will be what? For 10 number index, what will be the offset?
40, sir.
What? Okay, then the base address of the A array is in actually $A3. So is this perfectly clear to all of you? Is it clear? Please do respond.
Yes, sir.
Yes, sir.
Okay, so I am just giving you this solution in the chat box in case you need. Okay. So this was the last problem I was going to show you for this lecture. In the next class, we are going to cover. This is the problem we have solved. Okay, so in the next class, we are going to see branch instructions. Okay, branch on equal, branch on not equal, SLT, SLTI, and we're going to see some unconditional and conditional jump instructions as well. Okay, so if else related codes will be shown at first, then we are going to see some problems related to the loops as well, while loop. Okay, so we are going to cover all these topics in the next class. So we have seen up to this problem in this class. So can you guys please let me know if you have any question over what we have seen up to this class? No question? Okay, so I'm going to stop the screen share and I'm going to stop the recording as well, as I'm not going to let you know about any more new topic.